So we're doing chapter 4, part 2. Like I said, we're not going to jump right into the actual assignments on this. I want to talk about proofs. Okay, so bless you. Okay, so a proof is a series of statements and reasons that follow a logical progression to get us to a conclusion. Now, and it has to be a logical progression. I cannot prove something like, okay, I can't prove the sky is blue by saying, you know, given clouds are white, given there is a sky, the sky is blue because I said so. That's not logical, right? And I'm sure you've all experienced when your parents said, because I said so, and you went, that doesn't make any sense. But we have to follow logical progression. Now, the statements, these are equations, changes to equations, angle relationships, equality statements, like saying two things are equal or unequal, length relationships. So if you're talking, for example, about line segments or the sides of a triangle or the sides of a polygon or something. Let's see, what else might you say? Link relationships. Substitutions. Things like that. Okay? Now, the reasons are the things that allow you to do that. So they allow for the statements. And so reasons are properties. So you can have addition, subtraction, multiplication, and division. Those are all properties because you can add and subtract to both sides. You can have commutative, associative, substitution, reflexive, and we're going to go over all these properties, okay? So you can use properties, you can use definitions. So for example, if I have two angles that are vertical, I can say angle 1 is congruent to angle 2. That's the definition of vertical angles. So I can use a definition. I can use postulates. I can use theorems. And I can use corollaries. Okay. Now the postulates are things that we accept as true without proof. You know, like the corresponding angles in the parallel line postulate where the corresponding angles were congruent. Theorems are the things that we've talked about, the other angle relationships that we've had. You know, there's a bunch of theorems that we've had. And then the corollaries, we had that one perpendicular line corollary that follows from a theorem where it's just like, well, here's this added on little thing that, yeah, obviously that would mean that. So all of your reasons are going to be these things. They're going to be a property, a definition, a postulate, a theorem, or a corollary. And the reason allows the statements, and it's sort of like a what does that mean? You know, like I could say angle 1 is congruent to angle 2. Well, what does that mean? Well, it means they're vertical angles. You know, that sort of a thing. So you're answering the questions as you go through. Well, what does that tell me? Okay, that tells me this. What does that tell me? Okay, well, that tells me this. And you just follow through. Now, this is not, I say you just follow through, and you just make these series of logical. It's not a just. You have to train your brain to think this way. Proofs generally don't come naturally to people. Now, I'm not saying that there aren't people out there that there are people out there that proofs come completely naturally to. That are the people that all the math has been named after, right? So, if it's a struggle, if you can't wrap your brain around it, I don't want you to think like, oh my gosh, I can't do this. It's not that. It takes a while to train yourself to think this way. It's not natural. All right, so I want to review the properties that we'll be using in the proofs. Okay, you have the addition, subtraction, multiplication, or division property of equality. These are actually 4 different properties, but we'll just list them together. Okay. What these properties state is that I can add, subtract, multiply, or divide on both sides of an equal. And I don't change the truth. Well, how about if I write this and it's still true? Or false. If it was already false, like if you had a does not equal sign in the middle there, or an unequal. So this works for inequalities and all of them. So if you add, subtract, multiply, or divide, as long as you do it to both sides, you didn't change anything. You didn't change the truth of the statement. If it was true, it stays true. If it was false, it stays false. Okay? And those are properties that we can use in a proof. For example, if we were proving x plus 2 equals 4, x plus 2 equals 4, that means x equals 2. We would use subtraction because we'd subtract 2 from both sides. That would be our step. Okay. The next property that you have is the commutative property. And this property allows you to change the order. Of addition and multiplication only. Okay. So A plus B is the same thing as B plus A. A times B is the same thing as B times A, and if we use numbers, 2 plus 3 is the same thing as 3 plus 2. 2 times 3 is the same thing as 3 times 2. Now the reason this won't work for subtraction and division is because 2 minus 3 is not the same thing as 3 minus 2. 2 divided by 3 is not the same thing as 3 divided by 2. So it only works with multiplication and addition. That's the only time you can change the order. Sorry, my handwriting is sloppy today. The next one we have is the associative property. It only has one I in it. No, it doesn't. It has 2 I's, but not right next to each other. Okay, so we're going to change the groups of addition and multiplication only. If I have 1 plus 2 plus 3, and 2 and 3 is a group, that's the same thing as if I put 1 and 2 in a group and then I add 3 to it. This is 1 plus 5, that's 6. This is 3 plus 3, that's 6. If I do multiplication, I can still do that. 1 times 6 is 6, and 2 times 3 is 6. It's kind of interesting how they both turn out to be 6, isn't it? Anyway, division and subtraction won't work on this. But with addition and multiplication, you can switch around the groups. The reason you might do this is because it might make the addition or the multiplication easier. For example, if I have 7 times 13 times 10, 13 times 10 is 130. I might want to do that first and then multiply by 7. You know, just things like that that make it maybe easier to do the multiplication. So I would change that to 7 times 13 times 10. Again, it's a kind of a rearranging thing that you can use in your proof. You can kind of rearrange your groups because that might allow you to isolate something that you need to get to where you're trying to go, what you're trying to prove. Okay, so we've done commutative and associative. The next property we have is the distributive property. Okay, this is sort of just like kind of an allowing us to simplify things, really. The distributive property tells me that if I have any number outside, you have two types. You have over addition and over subtraction. If I have a times b plus c, that's the same thing as a times b plus a times c. And if I have a times b minus c, that's the same thing as a times b minus a times c. So it's 5x plus 10. And if I did 5 times x minus 3, that would be 5x minus 15. And what we're doing is we're literally distributing. You know, if you distribute flyers, you give one to everybody. We're distributing the 5. We give it to everybody. And that's the same if there's 2 things in the parentheses or if there's 20 things in the parentheses. You have to multiply every single one of them by whatever's outside. Okay. All right, so we've done commutative, associative, distributive. The next thing we have is identity. And there are 2 of them. We have the identity property of addition, and we have an identity property of multiplication. Okay, and the identity properties don't change anything. Okay. Basically what this says is if I have some number and I add 0 to it, it didn't change. Its identity remained the same. And if I have some number and I multiply it by 1, it didn't change. Okay. 0 is known as the additive identity. And 1 is known as the multiplicative identity. And you'll remember that one because your identity doesn't change, right? You are you all the time. So that's how you remember identity. Identity stays the same. So you can add 0 or multiply by 1. Following from the identity, we have the inverse. Okay. So the inverse properties give us the identities. Okay, so you have an addition one, and you have a multiplication one again. We want to get 0. So we want to add something to A that will give us 0. So we add negative A. For the multiplicative inverse, we want to get 1. So you multiply by the reciprocal. Okay, so here you have the opposite, and here you have the reciprocal. So negative A is the additive inverse. And 1 over A is the multiplicative inverse. These things come up a lot of times. Mostly it'll be like the multiplicative identity that you would use. Like when you give fractions a common denominator, you multiply the numerator and the denominator by whatever that same number, right? So if you want to turn if you want to turn halves into fourths, you multiply the top and the bottom by 2. Well, 2 over 2 is the same thing as 1. So you're using the multiplicative identity. The thing is in a proof, if I was trying to prove that I was adding 2 fractions together gave me something and I had to go through the steps to prove that, I wouldn't be able to give a common denominator without writing down a reason. Like I can't do anything. I can't add, I can't subtract, I can't do anything without having a reason. So to change the denominators to common, the reason is multiplicative identity. That's what allows me to do that. So that's why these kind of things will come up. They don't come up a lot, but I want you to have them in your list. So should you need them, you know what to do. Then we have the reflexive property. Okay. Reflexive, it sounds like reflection. Yes? Well, that's what it is. Reflexive property is identical on both sides of the equal. A equals A. 5 equals 5. Some side of some triangle equals itself or is congruent. It can be equal or congruent. Okay. What this does is it allows you to introduce new things. Okay. I can't talk about some side of a triangle that hasn't been mentioned previously unless I bring it into the proof. So you start with some given statements. That is your first things that you have. Like, that's like the flour and the eggs for the cake mix, maybe. Then you have to bring more stuff in sometimes. Like maybe you don't want just a flour and egg cake, maybe you want chocolate. So you bring the chocolate. Chocolate equals chocolate. And now you've brought it in, you've introduced it. So this is just the statement that allows you to bring something in. Anytime you need to bring in something new, you just say, oh, this thing equals itself, reflexive, ta-da! There it is. like magic. Okay. Then you have the symmetric property. And this just flips things around the equal. So if I have x equals 2, well then 2 equals x. It lets me turn things around if I need to for some reason. Because sometimes you need to do that. You need to turn things around to make it work. So this allows you to do that. It allows you to flip them around. Okay. You have substitution. And this allows you to take one thing out and you put something in with equal value. It's like change for dollar. You can take the $1 out and you can put the 4 quarters in. They look different, feel different, but they're the same, right? They're both worth $1. So this is what substitution does. If you know you have an x in there somewhere and you know that x is worth 5, you can take the x out and you can put the 5 in. Okay. So we have if x equals 2, I'm just going to give like an example. 3x plus 5 is equal to 3 times 2 plus 5. Okay, that's what it does. You can take one thing out and you can put something else in with the equal value. Every time anybody ever asked you to evaluate an expression for these values of these variables, that's what you were doing, substitution. Okay. Anytime you're going back and checking where you were, on those angle things where I made you solve for x and then tell me what the angle was, you were doing substitution. You didn't even know. If. Okay, transitive property. Okay, transitive property and substitution are very similar in what they do. They both allow you to kind of replace one thing with another. A substitution is a very direct. I'm taking this out and I'm putting this in. Transitive is more kind of, we'll get there eventually. It goes through a middleman. What transitive property says is if A is equal to B and B is equal to C, then A is equal to C. So we're taking the B out, but we're taking like the middleman out. Transitive property will always have this in the middle, where you have B and B, 5 and 5, you know, 3x and 3x. It'll always match. And what you're doing is it's called transitive property because you're transitioning from A through B to C. So it's not as a direct as the substitution property, but they both kind of do the same thing. They both take something out and replace it with something else. In this case, you're sort of taking out the B and just saying A and C are now equal to each other. Yeah, we talked about it a little bit, yeah. So this allows you this is basically you get from point A to point C. Right, so it allows you to say two things over here are equal to each other because you found out that they were both equal to some same thing. And you need that some same thing that's in the middle to be able to say the two outside things are equal. That's what that allows you to do. Last one. zero product property allows us to solve quadratics, should they ever come up. And that says if A times B is 0, then A equals 0 or B equals 0. And we use that to solve quadratics because we factor them out, and let's say we factor a quadratic and it gives us x plus 2 times x minus 3 equals 0. So then we say x plus 2 equals 0 or x minus 3 equals 0, and then we go from there. But to get from here to here, we're using this product property, the zero product property. So should the quadratics come up, this is what allows us to break them down and solve them. We'll start with some postulates. Okay, remember postulates are accepted as true. We have no proof. Okay. The first one says through any 2 points there's exactly one line. So if I give you any 2 points in space, you can draw only one line that'll go through both of those points. So here's the points. Okay, if I have 3 points that aren't in a line, any 3 points, there's only one plane that'll contain those points. That's a terrible plane. We'll just call it plane P. A line contains at least 2 points. Well, this one kind of makes sense because a line is infinite. And so if you have something that's infinitely long in 2 directions, it's going to have at least 2 points in there somewhere, right? And then we have a plane contains at least 3 points. And as we have discussed in the past, a plane is basically like a sheet of paper, but that it's an infinite sheet of paper that goes on and on and on forever and ever and ever into all eternity. Well, it makes sense that it'll have 3 points on it somewhere. And then the last one we have that says if 2 points are on the plane, which tells me that if I have 2 points and they're on a plane, and I draw a line through those 2 points, it is also on the plane. Right? So if I have a piece of paper that's my plane and I put 2 dots on it and draw a line on it, the line is not somewhere else out in space. It's going to be on the paper. This is why these are just accepted as true. They just sort of make sense. Okay. The segment addition postulate tells us if A, B, and C are collinear, so they're all on a line together, then point B is between A and C if and only if. Don't forget this IFF thing means if and only if. AB plus BC equals AC. So basically what you got this length here plus this length here equals the total length. That's what that tells us. Addition postulate. This is very similar to the segment addition postulate. This is what allows us to add angles, and that tells me if I have some angle ABC, point D is only in the center. If when I draw a line there, this angle plus this angle equals the whole thing. But this is what allows us, this allows us to add segments, but also to subtract. And this allows us to add and subtract angles. So in our proof, this is what allows us to do that. So you would just say angle addition or segment addition, even if you're subtracting. Because when you're subtracting, you're just adding a negative. So they just call it angle addition or segment addition. There's nothing called segment subtraction. Our statements that have been or need to be proved. Okay. Once they've been proven, then you can use them in other proofs. But until they were originally proven, you couldn't use them. Okay, so we have the supplement theorem. All right, so we have a linear pair, and a linear pair are any two angles, adjacent angles, that form a straight line. Okay, and the supplement theory is the thing that tells us that linear pairs add up to 180. Okay, so this is the theory that lets us, if you know you have a linear pair, this is the theory that lets you say, okay, these two angles are 180, and then you can go from there. And then we have the complement theorem. Okay, and so that's the theorem that lets you say, okay, if I have these two angles here, and this whole thing is 90 degrees, then the angles add up to 90 degrees. Okay, so the congruent supplement theorem tells us that if we have angles that are supplementary to the same angle or two congruent angles are congruent. So for the first part, supplementary to the same angle, if angle 1 and angle 2 is 180, and angle 3 and angle 2 is 180, then angle 1 is congruent to angle 3. Makes sense, right? Because they're both being added to the same thing to equal the same thing, so they would have to equal each other. And then the other one is if you throw in another angle. So if I say angle 2 is congruent to angle 3 to start out with, and then angle 1 and angle 2 is equal to 180, and then angle 3 and angle 4 is equal to 180, well, 2 and 3 were equal to each other, so that means angle 1 is the same as angle 4. Because they're being added again to the same thing, so that means they're the same. Okay, we're just going to stop there. I'll do the other one tomorrow.